Scene-aware foveated rendering. We propose a new scene-aware foveated rendering method, which considers the scene awareness and characteristics of the human visual system in foveated rendering. Here are two views on VR-HMDs. Compared to the state-of-the-art methods, our method achieves smaller errors in the fovea, periphery, salient region, and the whole image. The lower left of the left image shows our result, the upper right shows the full resolution rendering. The right are the close-ups of the rendered results. Foveated rendering can be achieved with the mapping-based framework, such as log-polar method. However, these methods are constructed only based on the visual acuity. Our method incorporates the scene awareness, visual acuity, and gaze motion into the mapping-based foveated rendering framework. Compared with the log-polar method, our results are closer to the full-resolution rendering results and preserve sharper details in periphery, especially in the area where the visual feature is high. When the gaze point moves, our method outperforms the log-polar method and has fewer jaggedness, such as the metal disc. When the viewpoint moves, our method outperforms the log-polar method and has less flicker, such as the metal horse. Besides, for moving objects in the scene, such as the red toy car, our method has sharper rendering results compared to the log-polar method. Our method has 3 steps. The first step is the conservative visual importance map generation. The second step is the pixel size control map construction. The third step is the foveated rendering. In step 1, we first generate the visual acuity map according to the gaze point and extract the visual feature map based on the G buffer. Then, we construct the conservative visual importance map by combining the visual feature map and the visual acuity map according to the gaze motion. In step 2, we first build a convolutional kernel according to the characteristics of human visual system. Next, the convolution is operated on the conservative visual importance map with the kernel to construct the pixel size control map, which guides the foveated rendering. In step 3, we first map the G buffer to a mapped G buffer with the guide of the pixel size control map. Then we render the results to a reduced resolution buffer based on the mapped G buffer. Next we do inverse mapping and map the reduced resolution buffer to a final full resolution buffer with the guide of inverse pixel size control map. In experiment, we compare our method with the ground truth and 4 previous methods. The ground truth is rendered with the full resolution. Our method and the other methods are rendered with the same compression ratio. HIP method renders 3 image layers around the gaze point with repeated rendering of the fovea region. Compared with it, our results are closer to the ground truth, both the fovea region and the periphery region. Log-polar method renders the image based on the kernel log-polar function. Compared with it, our results has less flicker, such as the table. Rectangular method renders the image based on the lens function. Compared with it, our results has fewer jaggedness, such as the street light. Rectilinear method renders the image based on the exponential function. Compared with it, our results has sharper rendering results, such as the motorcycle. To maintain the temporal consistency for the adjacent frames, we propose a temporal coherent refinement strategy. Here shows the comparison of the average interframe error, of the ground truth, our method, and the comparison methods. The brighter the image, the greater the interframe error. Compared with the previous methods, the results of our method are close to that of ground truth. Our method has smaller interframe errors in all regions. In conclusion, we proposed a scene-aware mapping-based foveated rendering method. Compared to existing state-of-the-art methods, our method achieves smaller error over the fovea, periphery regions, and the whole image with similar performance. Thanks for watching.